Hello friends, today we will study about higher order derivative. Higher order derivative, and this is the course of graduation final year derivatives. Earlier I have told you about the differentiation and the rules of differentiation. Now this is higher order differentiation. So since the derivative of a function uh, is also a function, therefore the derivative of derivative is possible. We find the derivative of any equation like x 3x to the power 4. So we can find the derivative of this. 4 into 3 is 12x to the power 3. Now we can also find the derivative of this also. Let us consider a functional relationship between two variables x and y, which is represented as, another example we will take, that y is equal to 3x to the power 4 plus 5x to the power cube minus 10x to the power 2 minus 4x plus 3. So let us consider this equation. If we want to measure the rate of change rate of change in y due to change in x, we find just derivative dy with respect to dx of this expression. So we will find out. So 4 into 3 is 12, and 4 minus 1 will be x to the power 4 minus 1 will be 3. So it will be 3 plus 15 x to the power 2, as 5 into 3 is 15 and 3 minus 1 will be 2. So x to the power 2 minus 2 into 10 is 20, and x to the power 2 minus 1 will be 1. So we will not write 1 as a power of x, minus 4, because 1 minus 1 is 0, so the x will be cancelled out, and 3, there is no variable, so it will not be written. The above expression can once again be differentiated. And this expression, when we differentiate, this is the first differentiation of the equation. If we differentiate this equation again, so this will be the second order differentiation. We will differentiate it as like dy with respect to dx. So we will differentiate this equation again. It will be d2y to dx square, that is 12 into 3 will be 12 into 3 36, and x3 minus 1 will be 2, plus 15 into 2 is 30, x2 minus 1 is 1, minus 20, x has no power, x1 minus 1 will be 0, so x will cancel out. In the terminology of calculus, we will call this expression as second differential coefficient of what? Of 3x is 4 plus 5x cube of this equation. 3x 4 plus 5x cube minus 10x square plus 4x plus 3 minus 10x square minus 4x plus 3. So this is the second differentiation. This was the equation, and the first differentiation is this. This is first differentiation, first differential equation or coefficient of, and this is the second differential equation. More specifically as dy with respect to dx. measures rate of change in y with respect to a small change in x. So similarly, d square y means d to y, we will call it d to y, and d square, it measures what? It measures the rate at which dy with respect to dx is changing with a very small change in x. In other words, dy with respect to dx measures the rate of change in y. In y is we have an equation like 3x4 plus 5x cube minus this. So as a rate of change in y is this when x changes marginally. So the rate of change in y when x changes marginally. So this measures the rate of change. Let us write it as it is better if you note it down, because there will be some confusion if you don't write it, because both are similar. You need to understand the things first. So let us see this y is 3x4 plus 5x cube minus 10x2 minus 4x plus 3. As x changes, this is changes, short form of changes, changes I mean changes. So rate of change in y as x changes. Now this is our first thing. Secondly, while another thing is d to y with respect to dx square, it measures the rate of change in y 3x4 plus 5x cube minus 10x square minus 4x plus 3 when x changes marginally. So rate of change in y, but here the x changes marginally, a very small change in x. In the same manner, we can go further for function derivative of third and fourth orders. This is our second order. This is first order. And this is second order derivative. In the same manner, we can go for further functions of derivative of the third order, fourth orders and others. So let us consider higher order derivatives and their notation. Higher order derivatives and their notation. So its notation will be y is equal to f is a function of x. So consider the same example again. 10x square minus 4x plus 3. It is a function first order derivative. This will be first order derivative, that is fx. F is a function of x, means second. Now the second order derivative will be d2y with respect to dx. So it will be like we differentiate the first function, first order derivative. and I want to rub this, let it line cleanly. So dy with respect to dx. So we differentiate the first order derivative again in the, it will be the second order derivative. So this will be f2 or second order derivative, or it will be like fxx. First one was fx, it was like, it was the fx. Second one was f double x, and third derivative will be d3y with respect to dx cube is equal to this. This will be third order derivative and third order derivative, and this third order derivative will be x cube. Here we have x double x, here we have 3x. This is the short form of third order derivative. Now move to the sign of derivative and the nature of the curve. How the let us consider sign of derivative and nature of the curve. We suppose we have a curve. This is y-axis, this is x-axis, this is y-axis, and this is our average cost curve. Here we have a minimum point, that is a minimum lowest cost output. At this output the cost is lowest. So this is our average cost here on the y-axis. We will, when we see that at this portion the cost is falling. Here it comes to minimum here, and then it starts increasing. So this is part 1 where the average cost is falling, and this is the part 2 where the average cost is rising. Here we have this, we call this lowest point as stationary point, which is a minimum point. And second, there is, when there is no change, is this is we call as stationary in economics. And second, also we can consider another graph of total product. This is our total product curve. You may have read in economics. This is x-axis, y-axis. On y we have output level. On x we have factors of production. Factors of production you may have known about it. And this is, we know that total product is maximum here. So this is maximum on this point, and this point we can call this as also stationary point. So here in the first part the total product is increasing, while in the second part total product is decreasing. Now let the sign of the derivative dy with respect to the nature of the curve represented dy by the given function. Suppose we have given two functions. So we can see the sign, first order derivative and second, and average cost and total products, which give graph as we have represented it above. We divide each curve into two parts, first part and second part. In the first part, at the minimum average cost curve, and the second part the maximum total product curve. Consider each part of each curve separately. Consider part 1 of average cost curve. First see the part 1 and part 2 of total product curve. In the part 1 of average cost, you can see the average cost is declining, while in the part 2 of total product curve, the part 2 of total product curve, you can see the part 2 of total product curve, the total product curve is declining. So in both the cases, the implement in variable factor x is associated with the fall in the average cost. Let us write in part 1 of average cost and part 2 of total product curve, where both are declining, we see. So in both cases variable factor x is associated with the fall in average cost and as well as total product. Hence the sign of the differential coefficient will be negative, because the average cost is also declining in the first part, while in the second part total product is declining. So when the things decline, so we will have negative and negative sign. Differential coefficient, their differential coefficient dx with respect to dy with respect to dx will be negative in both the cases. Okay, in both the cases their differential coefficient will be negative, as we have seen in the graph. It is also declining here in the first part average cost, in the second part total product, both are declining, so their differential coefficient will be negative. In the same, so in case of the second part of the average cost curve, let us see the second part of the average cost curve and the first part of the total cost curve. Is the second part of the average cost curve, second part, and this is the first part. Both are increasing. Here total product is increasing in the first part, and here the average cost is increasing in the second part. So let us, when there is an increase, let us see in part second of average cost and first of total product curve, sign of differential coefficient. What is differential coefficient? Dy with respect to dx will be positive. Its sign will be positive because of the average cost as well as the total product, because both average cost and total product both are increasing in here. So in the second part this average cost is increasing, while in the first part total product is increasing. So as they both increase, because TP and AC increases, this was increasing in the first part and this was increasing in the second part, so the sign will be positive. The relation of function with respect to its derivative gives us the following important properties of the derivatives. Now we will consider the properties of the derivatives. Write it down. The first derivative means what is the relation between the x and the y so first one is, if dy with respect to dx is greater than 0, then first derivative of the function is positive. first derivative of the function is positive. Curve rises from where? What is the position of the curve? Curve rise होता है कहाँ से? Rises from left to right. So the where this is positive, let us see. Here it is increasing, it is positive, it is decreasing, it is negative. It is decreasing in the first part, so it is negative, it is positive. So derivative will be positive. So when dy with respect to dx is greater than 0, when it is increasing from left, this is left to right. L to R. So this is increasing L to R. So it has a positive sign. Dy with respect to dx is greater than 0, then the first derivative will be positive. Now in second case, second property is if different derivative of dy with respect to dx is less than 0, then first derivative of the given function is negative. The curve means the curve falls from left to right. So consider when it is less than 0, the curve will fall. So in the total product curve, where it is falling, so from left, this is left and this is right. This is left. From left to right. So it is falling left से right में जा रहा है, it is falling left to right, and the first derivative of the function is less than 0. The function is negative. The function is negative because it is falling. It is falling from left to right, and the derivative will be less than 0. However, so respect to dx is less than 0, so derivative will be negative. Now third property. However, one question remain unanswered, that is what will be the nature of the curve if the derivative is neither 0 or neither greater than or nor less than 0. When dy with respect to dx is neither greater than nor less than 0 but equal to 0. So what will be the nature? So what will be the nature of the curve? Do you know? Dy with respect to dx is equal to 0 at any point. It means if it is equal to this at any point, it means that the rate of change in y with respect to x, with respect to small change in x, at that particular point is 0. To have a quantitative analysis or a graphical representation means there will be no change. So it will have the rate of change in y with respect to x at that particular point is 0, means there will be no change when this derivative is equal to 0. To have a quantitative analysis or the graphical representation, consider the following example. Now consider an example to have the quantitative analysis or the graphical representation as well. Suppose a functional relationship between x and y is equal to x square minus 4x plus 10. So when we first differentiate function y with respect to x, it will be 2x minus 4. So when we differentiate it again, but let us see first, this 2x minus 4 tells what? Do you know what it tells? It tells the slope. It tells the slope of the function. The first derivative will tell the slope of the function y is equal to x square, that is minus 4x plus 10. It tells the slope of this function. So when we differentiate this dy with respect to dx, 2x minus 4 is equal to 0. So let us find the value of 2x is equal to 4, and x is equal to 4 divided by 2, it will be 2. Function is in stationary state, so it means the function is in, our function is in stationary state. How so? Because from the above analysis of the first order derivative, as we have seen, the value of x is equal to 2. The rate of change is 0. How we can say so? Because when we substitute, it means the rate of change is 0 in the first derivative. How so? Because when we substitute 2 in the power 2 minus 4 is equal to 0. From the above analysis, the first order derivative of the function where the value of x is equal to 0 and the rate of change is 0, value of x is not 0, it is 2. So it means the function is in stationary state when the value. So in this connection, the important thing is that if the value of x is less than 2, if value of x is less than 2, sorry, or greater than 2, then what will be the slope? Here the x is equal to 2, but if the value of x is less than 2 or greater than 2, then what will be the slope? Any idea? So dy, let us check with respect to dx, we get the first derivative as 2x minus 4 when x value is less than 1. When x is less than 2, suppose x is equal to 1, so dy with respect to dx, it will be 2 1 minus 4, 2 minus 4, it will be minus 2. So our derivative dy with respect to dx will be minus 2, and when x is equal to 1.5, so the value of dy, with respect to dx, it will be 2 to 1.5 minus 4. So it will be minus 1. And when x is equal to 1.75, dy with respect to dx is equal to minus 0.5. So what can we conclude from this? All the values are negative. So, and these values are values are less than 2. 1.5 is less than 2, 1.55 is less than 2, 1 is less than 2. So in this case, what will you see when the value is less than 2? So in the derivative, conclusion will be, what can we conclude? We conclude if x is having value less than 1, less than 2, sorry, the rate of change is negative, is negative, and hence we can say that the function is falling from left to right. So now we can have a graphical analysis. With the function, we come to know the graphical representation or graphical representation. We come to know that what type of function. So now we can easily know what type of function we have, whether our function is negative or positive. So when the value is less than 2, here we can see first our graph is, here it is negative, here the value is less than 2, and here also our value of x is less than 2 in here, because the graph is declining. When x is less than 2, we can say that function is falling from left. This is left and this is right. Function is falling from left to right. So the value is less than 2. Now consider the case of x. Second case, when we see x is more than 2. more than 2 जब x ज़्यादा है 2 से. So when dy with respect to dx, take the same function 2x minus 4. So now substitute the value of x, which is should be greater than 3. Suppose when x is equal to 3, it is more than 3, more than 2. So when we take 3, so derivative will be 3. Substitute this in full, it will be 2, positive 2. And suppose when x is equal to 4, it is also more than 2. So dy with respect to dx will be, so 2 to the power 4 minus 4. 8 minus 4, it will be 4. And when x is equal to 5, dy, differentiate, consider the same. A substitute value of 5 instead of x, minus 4. 5 into 2 is 10, minus 4 will be 6. So this value, this value and this value, 2, 4 and 6, these are positive values. So it means our conclusion will be, if x is more than 2, rate of change will be positive. Rate of change is positive, and we can say, hence we can say that the function, derivative function, is rising from left to right, means our function is increasing from left to right. So through the equation we can have a graphical representation of our graph in this case. So what will be the value of our this is our average cost. It is at minimum, where x is equal to 2 as per the equation, the example we have taken, and in here the x will be more than 2, and here when the average cost is falling, the x will be less than 2. So this is a stationary state, there is no change, stationary point or turning point, we can say. Now according to the above values of the derivative, it is clear that the slope of the function turns out to be positive, which means the curve is rising from left to right. However, when x is equal to 2, what happened when x is equal to 2? We have, in the first case, where this is our first case, and there, this was the first case, this was the second case. So second case when x is more than 2, but when third case is what? When x is equal to 2, the curve is neither increases nor falls. As just for example, dy with respect to dx, take the same example, 2x 2x minus 4. So substitute the value of 2, as because x is equal to 2 minus 4, so it will be 0. So there is no change, and there is stationary position, which suggests that when value of x is equal to 2, value of y is not changing for a moment. So through the equation we can have a graphical representation, and we come to know that the graph is falling or rising only through the equation with the derivative, with the help of the derivative. Now consider an example of solving the derivative. Similar example, to solve the graph, to know the graphical representation and quantitative analysis. Y is equal to 10 plus 4x minus x square. So solution will be, we need to know graphical representation of this equation. So we differentiate y with respect to x, it will be 4, because x here is 1, and 4 into 1 is 1, and x 1 minus 1 will be 0, so there will be no power of x, will be removed, and here the 2x means x to the power 2, so the 2 will come here with the x, and 2 minus 1 will be 1, so no need to round the power with the x. We get the derivative, as we know 4 minus 2x, it is equal to 0. So we find the value of x as 2. Now suppose we substitute the value of derivative x, we substitute value of x, which is when x is less than 2. So when x, and this is dy with respect to dx. When we substitute the value in the above equation, when x is 1, so when x is 1, what will be the value of this? 2 into 1 is 1, and so it will be 2. 4 minus 2 will be 2. And when we substitute the value of x as 1.5, so what will be the value? 4 into 1.5. So what will be the value of this? It will be 3. 4 minus 3, it will be 1. And when the value is 1.75, 2 to the power 1.75, calculate the value. So it will be 4 this into, so it will be 0.5. Now consider the second case. Second case is when x is greater than 2, and take the same examples. dy with respect to dx. So here is 4 minus 2x. When x is equal to 3, that is more than 2, so 4 minus 2 to the power, not the power, 3, 4 minus 6 is equal to minus 2. And in the third, if we take 4, so substitute value 4 minus 2 into 4. So 4 minus 8 will be minus 4. So the value is minus 4. And the third case, if we take the 5, so 4 minus 2 to the power 2 means multiplied by 5. 4 minus 10, it will be minus 6. So these are the value. We get the negative values here, and we get the positive values here. When x is less than 4, we get positive values. When x is less than 4, when x is less than 2, we get positive values. When x is greater than 2, we get negative values. And from the table given above, it is clear that, write down the conclusion. So our conclusion will be, this is our answer of the equation. From the table given above, it is clear that when x is less than 2, when x is less than 2, the function is falling, but when x is equal to 2, OMG, sorry, when x is less than 2, so we have a positive values. When x is less than 2, जब x की वैल्यू हमने 2 से कम रखी है, then we have positive values, so it means the function is rising, increase हो रहा है, ऊपर को जा रहा है. And when x is greater than 2, जब x ज़्यादा है, जब x 2 से ज़्यादा है, I'm getting confused. When x is less than 2, most of the time I get confused with these signs. When x is greater than, greater इसीलिए होगा क्योंकि x की तरफ we have a mouth open, wide open towards x, so it is x is greater than 2. So write in bracket x is greater than 2. When x is greater than 2, the function is, So when we take the x value which is greater than 2, so the function is negative, it means it is falling. It is falling. The function is falling. Now when x is equal to 2, curve is neither increasing nor falling. It is stationary, or there is relative value. And there are some more examples we can also solve, but so let us take one more example. Another example we can take, example 3. Third example we can take is y is equal to 6x minus 3x square plus 1 upon 2x cube. We need to find out the quantitative analysis and the graphical representation of this. We need to find out the graphs. So we will derivate this function. It will be 6 minus 6x plus 3 divided by 2x square, because 1 by 2, this it will be 0. Assume it as equal to 0, and so it will be when we divide this, when we remove this 2, so it will be 12. We divide this, so 6 into 2 is 12 minus 6 into 2 is 12x plus 3x square is equal to 0. Or we can say, we can also write it as 4. We can take a common, we can take 3 common and can write it as 4x plus x square is equal to 4. So using quadratic formula, when we differentiate dy with respect to dx, it will be 4 plus minus under root 16 minus 16 upon 2 into 1. So it will be 4 plus minus under root 0 upon 2, and 4 divided by 2, it will be 2. So when the function is stationary, when function is stationary, value of x is 2. We get the value of x is 2. So now you can substitute the various values of x. We can substitute values of x and find the derivative. Suppose if we substitute 1, 1.5, 1.75, 2, 3, 4, 5, so we get various values of this, and through the values we can compare, and in this case the function will, you will calculate it yourself and find out the values. And in this case I am telling you the answer, the solution, that in that case neither the function has minimum nor the maximum value. It will be a point of inflection. Yes, one point is to be remembered, when there when neither when there is neither the function has minimum value nor the maximum value, it will be what? It will be point of inflection. So the, for example, this and this. So this, when this x is equal to 2, here it is increasing, x is greater than 2 when it is 2. So the curve is increasing but take a certain change in rising position. There is a kink and not decided as minima or maxima. Not decided as minima or maxima. Today this is enough for today, and we will, you may solve this equation and find out the graphical representation of this one, this example, and write in the comment section, and we will I will continue with the second derivative in the next lecture. So like and subscribe my channel. Thank you.